Hello and welcome to section 4.6, performing operations with complex numbers. In this lesson, we're going to take the imaginary unit, which we talked about earlier, and we're going to look how we use it in simple operations involving imaginary numbers. So let's go ahead and get started. And to first start, we're going to talk about what is a complex number. A complex number consists of any number, real or imaginary. So it's all numbers that you have ever seen before. All real numbers that you have ever heard of or seen of, and all imaginary numbers as well. So with that said, we need a way to write complex numbers. And they are written as a plus bi, where I, remember, is the square root of -1. This part right here is called the real component. This is the part of the number that's real. And this part over here is called the imaginary component. And so any number that you've ever thought of can be written in this particular form. For example, the number 7. 7 is a real number, we know, but it can be written in complex number form. 7 plus 0i. The number square root of -5 can be written as 0 plus square root 5i. That's an imaginary number, and it's written as such with no real portion to it. But we also have numbers that have both a real and an imaginary part to it. Something like that. So any number that you've ever heard of or thought of ever is a complex number, and it can be written in complex form. And we're going to be writing a lot of numbers in complex form, mostly because we'll be dealing with a lot of imaginary numbers. But just know that you can write any number in imaginary form, whether it's real or imaginary. So now that we know what a complex number is, we're going to start to deal with some of the operations with complex numbers. Adding, subtracting, multiplying, and dividing complex numbers. So we have two complex numbers here. Both of these have both a real part and an imaginary part. And so when we're adding complex numbers, what we do is we add their real parts and we add their imaginary parts. So we'd add their real parts, which is 4 and 2, which is 6. We would add their imaginary parts. -3 and 6 is +3i. Now, a lot of people see this and they see these in parentheses and they want to multiply them. But you have to be aware of what the sign is in between them. It's a plus sign here. Plus sign means we need to add them, not multiply them. So we're not going to FOIL. We're not going to do any of that. We're just going to add the real parts. We're going to add the imaginary parts. And that would be it. You'll see something similar here with subtraction. We're going to take the real parts and subtract them. So 6 minus -4 turns to 10. We're going to take the imaginary parts and add them. 2 minus -2 is 4i. So adding and subtracting are fairly simple when it comes to complex numbers. Now we're going to look at multiplying. Number 3 here is a multiplication problem. This imaginary number has only an imaginary part. This complex number has only an imaginary part. This complex number has both a real and an imaginary part. So what we're going to do, just like regular multiplication, we're going to distribute this -4i through the parentheses. So what happens then is we get -12i plus 24i squared. So with imaginary numbers, we never need to use an imaginary unit with a exponent higher than 1. Okay, because we know that we can simplify these imaginary units down. So -12i can stay the same, but we know that I squared is -1. Okay, because I is just the square root of -1. So when we square it, we get -1. And simplifying this out, this becomes -24. And it's just a good habit to get into when you're writing complex numbers to write the real portion first and the imaginary portion second. And so your answer for this one would be -24 minus 12i. All right. This multiplication problem we're going to need to FOIL, but we've done that enough times to know how to do it. And you'll see in this one we wind up with a similar situation where we have an I squared and we can reduce that I squared. Not only do we have an I squared, but we have a couple like terms here. So we can add 8i and -3i. And again, I changed I squared to -1. This becomes a -4 times a -1, a +4. And we can add it to 6. So that's 10 plus 5i. And again, it's written with its real part first and its imaginary part second. And so there was a couple of addition, subtraction, and multiplication problems. We're going to do one more multiplication problem, but it's a special type of multiplication problem. I want you to look at these two imaginary numbers. I want you to see if there's any relation between them. This one has a real part and an imaginary part. This one has a real part and an imaginary part. Really, the only difference between the two complex numbers is that it's a +3i and a -3i. And let's see what happens when we multiply the two. -2 times -2 is 4. -2 times -3i is +6i. 3i times -2 is -6i. And 3i times -3i is -9i squared. Oh my goodness, I don't know how to write and talk at the same time. I apologize. I said 3i times -2 was -6i, but for some reason I wrote -2i. Hopefully you caught that as well, but that should be a -6i. Okay, now once we get to this point, we're going to add like terms, and we're going to simplify down the I squared. 6i and -6i, well, that adds to 0i, or just 0, so it goes away. And I squared becomes -1. So we get 4 plus 9, which is 13. So one of the interesting things about these two complex numbers is that when we multiplied them, we started out with imaginary, and we ended up with something real. And this is the route in which complex numbers are actually useful, is that many times we can start with something imaginary and have it become something real. Just like with your imagination, something that you can imagine can turn into reality if you use it in the correct way. And so we just have to know how to use these in the correct way so that they can be useful. All right, so this idea that we just demonstrated here, multiplying two complex numbers with imaginary portions and getting something real, is called complex conjugates. And this is very similar to what we talked about with conjugates in terms of square roots. When multiplying complex conjugates, the imaginary becomes real. Sounds like the title to a Disney movie or something. But anyway, if you multiply two complex conjugates, you should end up with a real number. Complex conjugates look like this. A plus bi and a minus bi are complex conjugates. And here, I can even show you that this works. I'm going to multiply a plus bi and a minus bi. So when I multiply this out, a times a gives me a squared. a times negative bi gives me negative abi. Bi times a gives me positive abi. And bi times negative bi gives me negative b squared I squared. Simplifying, you can see that these middle two terms will cancel out. This I squared would become negative 1. And I'd be left with a squared plus b squared. And so even going a step further, if you are multiplying two conjugates together, it will always be the real portion squared plus the coefficient of the imaginary portion squared. So if you're multiplying a plus bi and a minus bi, it'll always be a squared plus b squared. So that's a pretty nice shortcut that we can take when we multiply complex conjugates. And so you might ask, well, when would we need to multiply complex conjugates? And the answer is when we are dividing by complex numbers. So just like with square roots, we do not like square roots in the bottom. And with this I down here, we technically have a square root in the bottom. All right, the square root is the square root of negative 1, but it's a square root nonetheless. And we don't want it in the bottom of our fraction. So what we're going to do is we're going to multiply the top and the bottom by, the complex conjugate. That's a minus sign. Okay, so I multiply the top and the bottom by the complex conjugate of the imaginary number in the denominator. So when I do that, on the top, I have to multiply 3 to both of these. 6 minus 12i. And on the bottom, I'm going to take a little shortcut. I know that if I multiply these two complex conjugates, I'm going to get 2 squared plus 4 squared. I don't even have to multiply it all out because I know, based on what I just did in the previous page, that anytime I multiply complex conjugates, it's going to be the square of the first plus the square of the second. So, simplifying that, I get 12 minus 6i over 4 plus 16 is 20. And from there, it's always best if you write complex numbers in terms of a real portion plus or minus an imaginary portion. Okay, so what I did is I split up the fraction into two fractions. All right, I divided 6 by 20 and I divided by 12 by 20. And those can be reduced. These are both divisible by 2. These are both divisible by 4. And you get your solution. 3/10 minus 3/5 I. And again, this has a real portion and an imaginary portion. And I always want you to write your answer like this, in simplest form and with a real portion and an imaginary portion. Okay, we'll try one more. Go through this one fairly quickly because it's very similar to number 6. So, need to multiply by the complex conjugate of the denominator. On the top and bottom, I'm going to have to FOIL. On the bottom should be easy because I know it's just going to be 3 squared plus 6 squared. Do a little simplifying on the top. Got some i's to add together. And I've got to turn that I squared into negative 1. On the bottom, I'm going to have 36 plus 9, which is 45. Do a little bit more simplifying on top. This negative 6 times negative 1 is going to become plus 6. Adding it to 18 gives me 24. And separating now, 24 over 45 plus 33 over 45i. And I think all of these numbers are divisible by 3. 6 over 15. So this one's divisible by, hold on. Each of these, hold on. So this would be 8 over 15. And this would be 11 over 15. There we go. Okay, and so that is simplified down into simplest form. Okay, so there's dividing complex numbers. So all we really have left is plotting and graphing complex numbers. And this is not too bad. When graphing complex numbers, it's very similar to graphing regular numbers. But with this one, our axes aren't an x and a y axis. We have a real axis, and we have an imaginary axis. So this is the real axis, and this is the imaginary axis. So, for example, let's say we want to plot, and let me get some marks on here. Let's say I want to plot these three imaginary numbers. 2 plus 3i, 4 minus 2i, and negative 1 plus I. Okay, so first we'll plot 2 plus 3i. You look at the real component, it's 2, and the imaginary component, it's 3. Essentially, to graph this on our imaginary graph, and again, this is an imaginary graph, it doesn't actually exist, but we can still graph it. We do 2 to the right, which is our real component, and 3 up, which is our imaginary component, and we'd put a point there at 2, 3. 2 being the real portion, 3 being the imaginary portion. For the next one, we have 4 as the real component. 1, 2, 3, 4. And negative 2 as the imaginary component. And so that would be B. C is negative 1 as the real component. And 1 as the imaginary component. So we'd go right there. So plotting these is not too difficult. All right, you just have to understand that what we're doing is we're plotting something imaginary on an imaginary scale. Okay, it's kind of crazy, but kind of cool at the same time. All right, and finally, to go along with plotting these, we can also find the imaginary distance from the axis, the origin, to the points. Okay, and if we want to find the distance from the origin to the points, that is called the absolute value of a complex number. So if you have any complex number w, where w is a plus bi, then the absolute value of w, which means this is the distance from origin of imaginary plot. The absolute value of w is the square root of the real part plus the imaginary part. So, for example, let's say I wanted to find absolute value of 6 minus 4i. The absolute value of 6 minus 4i is the square root of 6 squared plus negative 4 squared, which is equal to 36 plus 16, which is equal to the square root of 52. And I believe that is divisible by 4, so we can write it as the square root of 4 times the square root of 13, which is 2 square root 13. So that is the absolute value of this complex number. And again, it's an imaginary distance from the origin to the plotted point on the imaginary plot. All right, very good. So that is all for complex numbers for now. We are going to get solutions that are complex number for many of our quadratics in the near future. So it's important to know how to work with these complex numbers, and it's important to know how they can relate to solutions of a quadratic. Thank you, and I hope you have an incredibly amazing evening.